Okay, so I believe most of the people that had to connect are connected now. So let's begin this workshop about scanner headlights, and let's go. So the agenda for today is first of all an introduction about the headlights in general, the headlights um, work package. We'll be talking about the challenges you're facing as companies and the solutions we propose for to address these challenges. And afterwards, we'll deep dive into the scanner headlights pack, talking about the physics-based image rendering, the realistic material characterization, our real-time fog model, our capabilities in terms of interfacing with adaptive front light systems. Also, I'll be talking about the tools that we provide for the people that are addressing headlights use cases, and I'll be talking about how the integration is made into Scanner Studio. To start this journey, I'm gonna talk about how headlights projects were addressed a few years ago. So headlights projects could take up to 3 years to be released because of the long research and development phases. Companies had to plan along how much people would be needed for this project, how long it would take. They had to take these people, take them to northern countries in northern Europe in order for them to have more nighttime during during their work hours. Um, the the costs were high due to this because um, the companies had to make the people travel with their equipment. They had to work night shifts. The plannings were long, and there had many prototypes during these phases because simulation tools did not exist at the time, and physical prototypes were still the way to go. Also, what is not to be under considered is the risks that would undertake the employees of such companies because they had to do nighttime driving. They had to test prototypes during drivings. So these are things that cannot be under considered. What we understand from this phase is that you as companies are facing many challenges in these projects, in these headlights projects. First of them are saving money, optimizing the costs of developments, test and validation phases through the through various tools, and being able to reduce all these phases and have the most efficient product at the end. Also, reduce or nullify the number of physical prototypes until the release. So, which means that you would like to have as less as physical prototypes as needed, because physical prototypes, as everyone knows, cost very are very expensive from suppliers, and this need to be reduced. The number of these physical prototypes needs to be reduced. You are also facing challenges in terms of processes because you would like to perform various drives in night conditions and weather conditions, control these conditions, being able to test different kinds of vehicles, lighting systems in different kinds of environments, and being able to control this environment in order for you to accelerate once again the um, the the release of the product. And the time saving is one of the most important because something that is necessary for a company is to iterate faster on a project, reduce the validation phases, and reduce the time to market in order for this product to be um, in order for this product to be released as fast as possible for the end customers. At AVSimulation, we have understood this quite well because we propose a simulation tool that is called Scanner Studio. This is the main tool in which you will be designing the terrain on which the simulation takes place, the vehicle, the scenario, etc. You will be choosing the different actors in the scenario, whether they are vehicles that are driven autonomously via our traffic tools, or vehicles that are driven with a driver in the loop, uh, in simulator use cases, etc., and also the pedestrians revolving around the car, the different other vehicles, etc. Um, this is the main tool. Scanner Studio is the main tool, which comes also with a data set and a pack of modules that enable you to run a simulation and addressing basic use cases. But also we have a module catalog that you see a part of it here, and most especially the headlights pack, which is designed especially for the headlights use cases that we are talking about today. So this is the environment of Scanner Studio, and this can help you address many other use cases, such as, for instance, the AD-ADAS pack addressing the um, the ADAS um, the ADAS problems that revolve around the conception of the car, being able to feed representative information to your systems on the test via this pack, via what the virtual sensors are sensing, and retrieving these information, sending them to the system and the test. We're able to connect this also to the simulators pack in order for you to have a simulator environment with a driver in the loop, and being able to see how the driver feels during the drive of a particular model. And also the NCAP and regulations pack, which is really helpful when you need to homologate a vehicle in NCAP scenarios, whether it is Euro NCAP, US NCAP, China NCAP, Australian NCAP, etc. We have all these packs. The real-time targets also is important to connect actual hardware into the simulation. And last but not least is the physics-based sensor, which can help you um, provide to your systems under test and to your algorithms, to your image recognition algorithms, actual actual physics-based renderings of the virtual scene, and being able to feed them representative information during the simulation. So let's deep dive into the scanner headlights pack. And what I will be talking about first is the fact that this pack is a pack that allows you to render physics-based image for the headlights use cases. We are taking into account many layers of information from the environment, which go from the which go from how the scene is defined in terms of materials, with different kinds of layers of information on this. Through this physics-based image rendering, we're able to show an illuminance range into the simulation from 0.1 lux to 100 plus lux. And the physics-based rendering is vital to such rendering, because this is the most accurate one. We do not approximate what we think the light would do, but we approximate what the light actually does in terms of physical in terms of physics of the light. We calculate at any moment what the light actually does into the scene, depending on its its intensity, its direction, the material on which it is reflected or absorbed, etc. And given this, we're taking multiple light sources into account. because we're able to generate headlights that have many light sources as this one or fewer as this one, and also light sources of different types, going from the halogen to the LED types of headlamps. And why am I talking about this is because without this capability of physics-based rendering and the high dynamic range that comes afterwards, the dark parts are clipped to black into the scene, and the bright parts are clipped to white. So uh, because we have a high capability of calculating what the color of a pixel actually has to be, we're able to apply a linear tone mapping to match the display's dynamic. If you have a display that proposes a shorter range of colors, we're able to still have a representative simulation of this use case, the headlights use case, and actually see colors that are as close as possible to what would be in reality. Going from this, we are also able to render heterogeneous colors into the scene, because outgoing light distribution of the headlights are calculated from photometric measurements of the actual products, either from a physical product. As you can see here, can control we can measure what the actual light is, or if you have a numerical description of your headlamp in different kinds of software, you're able to extract this light distribution data from this software and incorporate it into our software. We're compatible with many file formats going for light distribution. So this is not a problem for us to integrate your light distribution into the software. Also, what is interesting to know is that a headlamp, especially LED headlamps, exhibit color heterogeneity, and this color heterogeneity can be measured and stored into the distribution file. It can be we store it um, in the software as a CIE XYZ format, which is an absolute format, before applying a tone mapping on it and having the actual color that would be rendered on the screen. This allows us to have a high fidelity color rendering into the simulation, and also allows color homogeneity evaluation when you are addressing these kind of use cases. So if you're not confident into the homogeneity of the headlamps product you are currently designing, this is the best. This is a good way to be sure of it. We have customers that have addressed these use cases. They took 60 virtual sensors into the scenario and have made into a simulation, and have made a real test drive on the actual terrain on which they performed the simulation, with the same sensors at the same spots, and the delta of the measurements was really low, and the comparison was real representative between the two. So this allows you to address these kind of use cases. And this is also possible because the headlights pack allows to incorporate realistic material characterization into the virtual scene. So the light the light perception, as we know, depends on different factors, whether it is the material on which the light is reflected or absorbed, the viewing angle of the person that is looking at the material, the light spectrum of the light itself, and many others. And at AVSimulation, we use a BRDF function in order to characterize each material, define how the light is reflected on this surface, on this specific surface, which goes to this representation here. Here you have the BRDF of a dry tarmac from a so the light ray hits in at this point in the middle, and all the other is the representation of how the light reacts to this light ray. And here we have the representation of a wet tarmac in terms of color rendering. So you see these are quite different, and we're able to incorporate this difference into the environment itself in order to have the best headlamps simulation possible. And to do this, we have a toolbox directly incorporated into Scanner Studio, which allows you to incorporate your textures and your BRDFs directly to the terrain, which is quite powerful because during the time you're creating the terrain on which the simulation will take place, you're able to incorporate these BRDFs and have them stored into the terrain, whether you're using the headlights pack, or not. And this is also compatible with real-time rendering, which means that all this information about the how the light reacts will be displayed real time during your simulation, during actual drives, and you will be able to see this difference, as we can see here. With the BRDF, the lights is a little bit dimmer compared to without BRDF, where the light is scattered as um, no matter what the material is. We also incorporate into the simulation a real-time weather model because we think that our customers need to have control on the conditions on which the headlamps simulation takes place, because this is really important to make the best possible product. We can handle clouds in the scene and the moonlight. So these are two factors that can be taken into account during the addressing of these headlamps use cases. We also take into account different kinds of weather condition, the fog, the rain, the snow, and all affect the way that we perceive the light during a simulation, during a real drive. Our fog model, as you can see in the video, takes into account the attenuation of the light, the light halos that are produced from hitting in a fog environment, and also the veiling, which is the backscattering of the luminous energy on the suspended water into the air. And this is really a good way to control all these conditions, being able to address these use cases into a representative scenario, in a representative environment, and being able also to drive these vehicles into these situations. So either if you're addressing either if you're addressing specific headlamps problems for designing your headlamps product, or if you're addressing human factors use cases which have to be into a real drive with bad weather conditions and different kinds of um, events occurring during the drive, you're able to do so with this because it is optimized for the real time, and you're able to control these events and these weather conditions. Also, what is interesting to point out is that we have the capability into the 9 Test Manager, which is the main module that comes with the headlights pack, to retrieve information, representative information from the simulation, from the AD-ADAS or the physics-based sensors pack. Give this information in terms of obstacles, objects, vehicles, pedestrians surrounding the vehicle, or directly, if we're talking about the physics-based, directly the representation of the environments in terms of physics, whether it is for a radar or a lidar. Give this information directly to your system under test, which would be um, a matrix beam or a pixel lighting, etc. So we would be able to give the vehicle status, the driver, the different driver commands if you have a driver in the loop, and the sensor outputs to a input output manager that would have to be designed by your teams in order for it to feed represent information to your system under test, whether it is a model in the loop, a software in the loop, or a hardware in the loop directly, because we're capable of connecting with MATLAB Simulink, these kind of use cases. Uh, if you are using software in the loop, we're able to directly incorporate compiled versions of your software into the simulation loop. And if you want hardware in the loop, the real-time targets pack allows you to connect to different kinds of networks, such as CAN networks, in order for it to feed information to your vehicle. And afterwards, when your system under test has been fed with representative information, it generates a representative it generates, sorry, a control command for the different projectors of this headlamps product. And these information would be controlling the actual headlamps. Each and every light source into the simulation is controllable in terms of head, pitching, yaw, intensity, etc. These elements would be taken into account into the simulation in real time, and we're able to address how these use cases react. This can be used either to design, evaluate, validate your headlamps products, or to address human factors use cases when you have a driver in the loop for your system and the test. And also keep in mind that we have rich and representative environments that can be incorporated into the simulation. We're able to take into account the rolling surface, the different kinds of curvatures, banking of the road, etc. The actual physical and optical materials, different kinds of actors, different kinds of events. So this is really a representative simulation that can be with which you can test and validate your headlamps products. And as you can see here, this is connected directly to Simulink, for instance. In this pack, we have different kinds of tools that are especially made for headlamps engineers in order for us to help them design the products and iterate rapidly on a headlamps product. So first of all would be the customizable aiming walls. We have some default aiming walls that are incorporated into the simulation, but you can design your own aiming walls with different kinds of lines, different kinds of uh, of angles of the on this aiming wall, different distances, etc. So This is a tool that's provided and can be used to address how your product is designed. We also have customizable measurement grids in order for you to address how your once again how your product is designed and at which where it it I would say shines. We're able also to display in real time the Isolux curves with mouse picking, so you're able to pick on the screen each any point uh, on the screen, and you would be able to see how much light is emitted there, the intensity of it. We have 2D photometric distributions, so we're able to generate those from the photometries and the different kinds of um, headlamps products. And also we have virtual sensors that will display the quantity of lux of candela and the Deboer scale live on each virtual sensor placed on the scene. So by default, we have virtual sensors that are placed on each vehicle at strategic points. For instance, the eye point of the driver, one in the front also of the vehicle, and two in the back. Three in the back, sorry, one in the middle, one in on right wing, and one on left wing. So this is really a very powerful tool in order for you to record during the simulation how much light is sensed at a specific point, and in this case, you would be able to tell if your light product is designed correctly. And keep in mind that this um, this toolbox and this pack is also compatible with massive simulation, so available in Scanner. And you're able to automate your test, generate a test plan from a specific scenario and divert from this scenario in order for you to have a batch of scenarios you want to address. And you can execute these scenarios on a cloud environment to accelerate the execution and have the results faster and automate the actual analysis phase of the results. So this is a very powerful tool if you want to address many use cases, if you want to test many products, many hypotheses during your design phase. And now that we've talked about the headlamps pack, keep in mind that Scanner Studio is not only a headlights tool. It is mainly a simulation tool that will with which you will be able to addressing many use cases coming from the automotive world. So if you want to use the same tool between all of your teams, it is possible because we can address headlight systems, headlights use cases, ADAS use cases with the capability of our representative sensors. If you're designing automated driving vehicles, we're able to address machine learning scenarios, etc. So this can be used along the whole cycle of development of your vehicle between all of your teams that would be using this one and only tool, and would be able to exchange data and perform simulations with with the different systems they are designing, and in the end build the actual vehicle that will be driving on open road, and will be able to drive this into simulation in a representative environment. And also keep in mind that these scenarios can be run on different test platforms because Scanner is compatible with many test platforms, going from the workstation through the different kinds of simulator, whether they are compact or high performance. We're able to connect vehicle in the loop, hardware in the loop, or run scenarios on HPC or cloud environments. So this is really a powerful tool for you to have digital continuity between all your teams, and to be able to perform simulations on many test platforms, as many test platforms as possible. And I think we're done with the presentation of the headlights pack. So what needs to be remembered from this presentation is that the headlights pack includes the capability to design your headlamp system with as many projectors as you would need, as many light functions as you would need, low beam, high beam, fog beam, etc. You're able to design this very precisely because we can incorporate as many light sources per projector, and as many projectors per product. You're able to switch live between them during your simulation, so you can compare this really quickly. We're capable of interacting with advanced front light systems, thanks to the capability of Scanner to connect to C++, C++ programs, MATLAB Simulink programs, other environments such as real-time environments for hardware in the loop simulations. So if you want to connect directly your final product to the simulation and see how it would react coming from representative information, it is totally possible to do so. Uh, this is a physics-based calculation, so the results of this simulation are really powerful, are really representative, and as close to the reality as they get. We're proud of this because this is something that we have worked uh, uh, along the years on, and this is really a strength of the headlights pack. This is possible thanks to the incorporation of directly the photometries of each light source, coming from file formats that are FTA, HLT, IES, ATF, etc. We're able also to incorporate the actual color distribution of the headlamp. So this is a tool you can really trust in terms of color and in terms of light intensity at each point. And of course, we have an analysis tool that can help you analyze the results of your simulation, extract data from it, either compute it directly into our software or use third-party softwares to analyze this data. So this is really a powerful tool for you to have during the analysis phase. And keep in mind also that it works with Scanner's foundation pack. So this whole tool chain is integrated into Scanner and can perform like complex scenarios, complex drive scenarios, going on rich environments, including AFS strategies, aiming walls, different kinds of scenarios, actors, vehicles in the loop. So this is really, this is not only a lighting simulation tool, it is also a simulation tool for the whole vehicle and uses the same data coming from this simulation. Now that I have presented you all of this, my call to action for you would be to, if you want to test this headlamp spec or Scanner software, you can go to our website at avsimulation.com/free download, and you can request actually a Scanner Studio trial version for you to have in your company, test how the software is, and we are providing assistance during this evaluation phase. So feel free to contact us. And also, if you want to accelerate your evaluation, we propose a samples pack for those of you that desire an evaluation, in which we incorporate many use cases and many examples of how it is implemented into Scanner. So if you want to test the software and quickly see how to connect your systems, it is totally possible to do so thanks to the samples pack incorporated into the trial version. Thank you very much for attending this workshop.